Okay, so let's look at this second example. And I need the first derivative. That's going to be 4x cubed plus 24x squared plus 36x plus 12. And then I'm going to take the derivative of the derivative to get the second derivative. 12x squared plus 48x plus 36. So now I'm going to set this equal to 0. So don't forget your tall vertical line for set this equal to 0. And I noticed that I have a GCF of 12. So let's factor out the 12 and get x squared plus 4x plus 3 equals 0. And remembering that multiplying by a constant in the front doesn't do anything about changing the zeros, so we can ignore it, in fact. And then we're going to factor and get x plus 3 and x plus 1. And then we're going to use the zero product property that says either x plus 3 is 1 or x plus 3 is 0 or x plus 1 is 0. And so that gives us our two important numbers we need to analyze. So when x is -3 and when x is -1. Those are our points of interest. We already used the phrase critical numbers when we were talking about the first derivative, and nobody has made up a good phrase for the important points of the second derivative, so they're just important points of the second derivative. So let's put them on this number line. I have -3 and -1. And then so far what I know is that the second derivative is 0 at -3 and 0 at -1 because that's how I found those numbers. So let's leave room to put our information about the function and then check our intervals. And we're checking the second derivative to see if it's positive or negative. So my first interval is from -∞ to -3. I'm going to use -10. So I'm going to have f double prime of -10 equals 12 times -10 squared plus 48 times -10 plus 36. And I don't care what this number is. All I care about is whether it's positive or negative. So I can see that it's positive. Feel free to do the calculator work to convince yourself. Please don't guess. That's a really bad idea. So the second derivative is positive everywhere in the interval from -∞ to -3. Okay, so now let's check from -3 to -1, and I'm going to use -2 for my test point. So f prime of -2 is 12 times -2 squared plus 48 times -2 plus 36. Well, now I can see that this is negative. Go ahead and verify that for yourself. Don't take my word for it. And then our third interval is going to be from -1 to infinity. Oh, and we can use 0 in this interval, and f double prime of 0 is just going to be the 36, so that's positive. So now let's see what conclusions we can draw about f. So we can see it's concave up, and then it's concave down, and then it's concave up. And then because we have the pattern of concave up, second derivative 0, concave down, this means we have an inflection point at x equals -3. And then as we move more towards the right, we see we have the pattern of -0, positive for the second derivative. So that means we also have an inflection point there. So let's go ahead and write our answer to the question here. F is concave up on the interval from -∞ to -3 union with the interval from -1 to infinity. F is concave down on the interval from -3 to -1. So for every x value between -3 and -1, you have downward concavity. And then we can see that we have inflection points. So F has an inflection point when, and you can either say when or at, when x equals -3 and when x equals -1. So they're not actually asking us where the inflection point is, so make sure you pay attention to the directions. It says find the location. This means just find the x values where this happens. I tend to be what I think is more clear on my instructions, and I will say, what are the x values where the points of inflection occur? Okay, so let's look at this graph. Here we go. And on Desmos, it's easy to see where the mins are. Desmos, in fact, will point them out for you. So here's a min and a max and a min. Sorry, go away. And so we can see that between this local min and local max, that's where we found the inflection point. And let me scoot this down just a little so you can see that the inflection point we found was at -3. So I'm actually going to draw the line x equals -3 just so you can see that the gray dot is where the concavity is changing from being concave up to being concave down. And then at x equals -1 was where we said the concavity is changing from concave down to concave up. So let me strongly encourage you to do the math work and look at the graphs and make sure it's all coming together for you. So one really important application of the second derivative is something called the point of diminishing returns. And you may have learned about this in an economics class or some other class. It's an important point because it kind of says you should stop using up your resources doing this now because you're not getting as much return as you were. Your returns are diminishing. So it's a specific application of the inflection point, which your book likes to call the point of inflection. And the concavity changes from concave upward to concave downward. And in fact, the first derivative has to be positive everywhere. So you're increasing, but you're first increasing at an increasing rate at the beginning of whatever's going on. And then you switch to increasing at a decreasing rate. That point where the switch occurs is an inflection point, and it has a specific name of the point of diminishing returns when it's in this scenario. So let's look at an example where R represents revenue in thousands of dollars, and X is the amount you're spending on advertising in thousands of dollars. So let's find r double prime of x. So the first derivative, here's the r function. The first derivative is going to be 72x minus 3x squared. And then your second derivative is the derivative of your first derivative. That's going to be 72 minus 6x. And we want to know when that's 0 because we're looking for inflection points. And that's going to happen when x equals 12. So here is our divider, x equals 12. Well, we want to make sure that on either side of this point, the first derivative is positive because we have, r is increasing. Oh, r prime, I said it right. R prime is positive, so r is increasing. So let's look at our first derivative and see what we can figure out here. Here I see a GCF of 3x. And that looks like 24 minus x is left over. And so my two critical numbers are x equals 0 and x equals 24. So I have a point over here of 0 and 24. Okay, so we're going to need an extra row on this diagram. So r prime is 0 when x is 0 and 0 when x is 24. Then r double prime is 0 when x is 12. Okay, so we first want to verify that r prime is positive when x is 12. So let's do r prime of 12. So it's going to be 3 times 12 times 24 minus 12. And that's obviously positive. So everywhere in this interval, the first derivative is positive. So now let's look at the second derivative. And we're going to look at the interval from 0 to 12 and test 10. And we're looking at r double prime. Is it positive or negative? So we're going to look at r double prime of 10. 72 minus 6 times 10, that's positive. Then from 12 to 24, let's pick 20 and see r double prime of 20 is negative. So now let's look at r. From 0 to 12, r is increasing. That's the r prime positive at an increasing rate. That's the r double prime positive. And then it's increasing at a decreasing rate. So at x equals 12, this is a point of diminishing returns. So the point of diminishing returns occurs when $12,000 are spent on advertising. So it's saying that's the best you're going to do with how much you're getting for your dollar. And after that, you can keep spending on advertising and your sales will keep going up, but not at the same rate that they were. You're getting less bang for your buck, less increase for your dollar spent on advertising. Okay, so I'm going to pause here, and the last movie we'll talk about max and mins.